let's start with a few parameters. So let's say this is our object, just a mark, and this camera plays our point of view. So our first parameter is the true size of the object. I'm using this mark. So for true size, I just measure this diameter, which is around 4 inches. Okay? We use S for true size. So in this case, S is 4 inches. Just this size, side to side. But there is another size which is called the angular size. And angular size is basically the angle this observer sees this object. Okay, so it is something like this. This is our point. This line goes here. This line goes here. So actually, this is the angle I'm talking about, which is theta. We use theta or we use pi. So theta or pi is the angle. And let's say this angle is 30 degrees. And first thing you notice is this unit. This angle could be measured in degrees. So it is degrees or radian or arc seconds. Degrees, radian, or arc seconds. And finally, we have the distance, which distance is basically from here to here. So in this case, distance is, let's say I use the center, distance is around 10 inches. So D is around 10 inches. Okay. For most of these cases, we don't care about the unit of distance and true size. We just keep them the same. So if this is in inches, we use inches for distance. If this is in kilometer, we use kilometer for distance. Okay. So we have true size, we have angular size, and we have distance. Okay, now let's talk about the relationship between these three parameters. Let's start with the true size. What happens if I change this true size? So if I change this true size, if I decrease or increase this true size, the angular size will also decrease or increase appropriately. So for example, if I double the size, this angular size is also doubled. If I halve the size, this angular size is also divided by half. This is first relationship. Now, let's say I keep this true size a constant number. So this is just true size, one object. And if I change the distance, so if I change the distance, if I move this object farther away, the result is a smaller angular size. This is now what I see. Okay? So if I increase the distance, the angular size will decrease. And so on and so forth. So we can play with these parameters to see what happened to the other one. But in summary, the formula is D is equal S divided by theta. This is our general formula. So distance is equal to true size divided by angular size. So it means this distance is equal to this size divided by angular size, But be careful, this angular size should be in radian. But we usually measure this angle in degrees. So theta in radian is theta in degrees divided by 57.3. So you have to convert theta from one unit to another unit. And in general, we prefer radian. But don't worry about S and D, because whatever number you use for S, whatever unit it is, it's the same unit for distance. So if this is in kilometers, this will be in kilometers. If this is in miles, this will be in miles. Now let's talk about parallax. Parallax is a very useful technique to measure distance between point of view and star. But we need a background star as a reference, so this is a second object. The main idea is, if we move around, the relative angle between foreground star and background star will change. You can see what's happening in this case. I'm moving toward this side and this side. Okay, so looking from different points, I will see different angle between foreground and background, and this shift in their relative position is called parallax. You can see in this case, this is foreground, this is background, and this is the angle you see. If I move here, basically there is no big angle. If I move here, again you can see this is the angle. Okay, so this angle depends on our point of view, and this is simply parallax. Okay, now let's see how we use parallax in real world. In real world, we need a big base for our parallax measurement, and for base we use our solar system. So let's say this is the sun at the center and Earth is orbiting around the sun, and the best way to do this parallax measurement is to measure this angle at a given time, then repeat this measurement 6 months later. So basically we are using a triangle, and our base is 1 AU, which is the distance between, the average distance between the sun and Earth. Okay, and that's the idea. So we do one observation at this point, then 6 months later we do a second observation from this point, and we take this average angle and we find this parallax angle. Okay, and using that parallax angle we can calculate the distance between our solar system and a specific star. So our goal is to get this distance d. So don't worry about the background. This background is just as a reference. Now how we do this calculation? So if you're using this configuration, the distance is simply d is equal, and in this case our true size s is 1 AU, 1 divided by this parallax angle in radian. Okay, so this is 1 AU divided by parallax angle in radian, so it means this distance is in AU. So this is one way. If we have parallax angle in radian, we can calculate distance in AU. There's another unit which is more practical. What we usually see in the sky is this parallax angle is given in arc second. and arc second is basically 1/60th of arc minute. 1 arc minute is 1/60th of 1 degree. So it means if you take 1 degree and divide by 60, you get 1 arc minute. If you take one of those arc minutes and divide by 60, you get 1 arc second. We can do 1 divided by parallax angle in arc second. So anytime you see this sign for angle, it's in arc second. And what you get is distance in parsec. Okay? So it's the same formula, but it depends on the main unit you use for parallax angle. If you use radian, you get this distance in AU. If you use arc second, you get this distance in parsec. And then you can convert between all of these units. Okay, now let's look at this flowchart of your progress. The main idea is how to get distance using a given parallax angle. Okay, so you start from this point, you have this parallax angle, and you should look at your final number. If you are looking at distance in AU or kilometer, you should go this way. And if you are looking at this distance in parsec or light year, you should go this way. AU and kilometers are more tricky. You need more calculations. So let's go this way. So you start from parallax in arc second, whatever number you have in arc seconds. For AU and kilometer, you need parallax in radian. So first, you have to convert from arc seconds to radian. But there are 2 steps. First, you have to convert from arc seconds to degrees. Then you have to convert from degrees to radian. And finally, you can use this parallax in radian to get this distance. So you take that number in arc second, divide by 3600, and you get parallax angle in degrees, which is very small number. Because remember, arc second is very small unit. Then you have this number in degrees, take that number and divide by 57.3, and you get parallax angle in radian. Now you have parallax angle in radian. Remember, distance in AU is simply 1 over pi in radian. That will be distance in AU. If you need distance in AU, this is your final step. But if you need distance in kilometers, you have to go 1 step further and take that number in AU and multiply by 150 million. Then you get distance in kilometers. And keep all of these numbers. You can go in different direction. You can do different conversion. But I believe this is the simplest way you can find your distance in different units. And this is the minimum calculation you need. Okay, so convert from arc seconds to radian, 1 over radian distance in AU, then multiply 150 million, you get distance in kilometers. For parsecond light here, you don't need to convert parallax. So take that parallax, 1 over parallax in arc second is simply distance in parsec. And distance in light year is simply 2.26 times distance in parsec. That's the main reason a lot of people use parsec and light year in astronomy, because these are easy numbers to deal with. Also note that for distance in light year, this is distance, but it has something to do with time. Because anytime you say this specific star is at 10 light years away, it also means it will take 10 years for any light to travel from that specific star to Earth. Okay, so this is distance, but it also has a time meaning. This is your flowchart to do these calculations.